Answer this question. Let's say you have a full wave rectifier circuit with this waveform as its output signal. How do you transform this output signal into a DC signal? If you already have an answer to that question, feel free to leave a comment on this video. If you don't know, however, stick around until the end of this video to find out. A rectifier in electronics is any device or circuit that converts an AC signal into DC. Rectifiers are quite popular, particularly in most gadgets we use daily, including smartphones and computers. Rectifiers in these devices convert the AC power supply from the wall to DC to be able to charge their batteries. Rectifiers are also used with transformers to help achieve a desired DC voltage. Some rectifiers, such as the full wave rectifier, which we'll be talking about in this video, can be used to power up simple devices such as a motor or an LED. Before moving on to the circuit of the full wave rectifier, the term rectification simply refers to any process that changes bidirectional flow into a unidirectional flow. We all know the typical AC signal flows in both directions in a circuit and can be modeled with a sinusoidal wave. Depending on the type of rectification used, the output signal will either look like the waveform we have here in A or B. The rectified signal in A indicates that the full wave rectification method was used, and B shows a half wave rectification. As you can observe for the half wave, the signal output only contains the positive portions of the input signal. In this video, I'll explain how this waveform can be achieved and go further to describe how we can make it look like the typical DC signal. Let's get into it. This circuit for the full wave rectifier, also called the center tapped rectifier, usually looks like this. On the very far left, we have our AC source, which is where we get the name of the rectifier from. It's called a center tap transformer because its secondary coil is divided into two equal parts with the center tap grounded. The remaining terminals of the winding are connected to two diodes, and the load of the circuit is connected to the node between the cathodes of the two diodes. Now that we have this, let's talk about how full wave rectification is achieved with this circuit. Since we have an AC input, we'll analyze each half cycle one at a time. For the first half cycle, the diode D1 is forward biased, while the diode D2 is reverse biased. This will short D1 but open D2, and since we're using a center tap transformer, we'll have a signal with half the amplitude of the input source flowing through the diode to the load. The amplitude of the signal at the load will be Vp, which is the peak voltage of the AC signal, divided by 2, minus 0.7, which is the typical voltage drop across a diode. Now, during the negative cycle of the AC signal, diode D2 is forward biased and diode D1 is reverse biased. The current from the source will flow through D2. The waveform at the load will also be Vp divided by 2, minus 0.7. Now the waveform will now look something like this, which can loosely be interpreted as the absolute value of the input sine wave. Now because we use a center tap transformer, the output waveform has an amplitude half the input signal. Since the rectifier produces an output during both cycles of the input signal, it has twice as many positive cycles. As a result, the average value of our output waveform will be equal to the average value of our AC signal. Although the signal has now been rectified, we still have a change in voltage at the load, even though we want a straight DC voltage. Now, if you didn't know the answer to the question I asked earlier on, this is where you find out. To fix the ripple, we add a capacitor in parallel with the load. This capacitor, sometimes referred to as smoothing capacitor, converts the rippled output of the rectifier into a smoother DC output. The capacitor is able to help us achieve this due to its ability to store charges when the rectified signal is rising and maintains the same voltage level across the load when the signal is falling. Depending on how high or low the capacitor value is, we can have lower or higher ripples respectively. The relationship between the capacitor and the amount of ripple left can be seen in this equation. V ripple is equal to the load current divided by the frequency of the signal, that's our rectified signal, times the capacitance. If you found this video valuable, hit the like button. Also, I make electrical engineering tutorial videos like this one, so be sure to subscribe and hit the bell for notifications so you never miss a video. Thank you for watching, and I'll see you in the next.